Okay, so sorry, I forgot to put on my better microphone. Hopefully the audio is better now. And we will move on to look at acceleration, which is the last of our key players in this. And we can start putting all these together and see if we can make predictions about motions and what happens in the future if we know the present, right? Okay, so we just looked at velocity. So roughly speaking, right, it's the change in displacement over time taken. But more precisely, if we write it in mathematics, that's actually pretty precise as well. But just in terms of mathematics, we have average and instantaneous velocity. So when we say velocity, it's sometimes vague. You might want to clarify. Actually, when we say velocity, usually we mean instantaneous. We mean the velocity at that moment. Okay. And if we mean average, we usually will specify average. That's usually the case. But in any case, we understand average, you take the total displacement, divide by time taken. Instantaneous, you need to take the displacement at that point, but it doesn't make sense to say displacement at that point, right? So you still take a little bit of average, but then you shrink the time to zero. So the time that you're investigating to almost zero, you take the limit of it to zero, right? That is the instantaneous there. And we replace that with the notation dx dt, because we're lazy, we don't want to write this, so we just write this, right? Okay, so now we can just keep that over there. We can generalize this, right? Or sort of move, I should say, move to the next step and look at acceleration, and we can use the same concept. We can define average acceleration and instantaneous acceleration. And this time, instead of a change in position, or right, this is the change in, I should say change in position. Position, which is the total displacement, right? We should look at the change in velocity. So we can look at that, right? So how much does the velocity change in a given time? So that's the average over a given time, or I can look at that instant, which is the limit of delta t goes 0 of delta v delta t. Okay, so what that means is exactly the same thing, right? So if I have the velocity changing, so this time I'm going to draw, I want to analyze the change in velocity. Let's make that clear as well. So acceleration is basically the change in velocity, right? Change in velocity over the time taken. Okay. So this is most rigorous. I'm just saying roughly, because it depends. When you say acceleration, it depends on which one do you mean, right? So this is the change in position over the time, and change in position, we give it a name, call it S. We call it displacement. So the displacement over time, but we don't have a special name. Thank God for that. We don't have a special name for change in velocity, so we just call it change in velocity over time taken. So if we want to analyze the change in velocity, this time let's plot a velocity time graph, right? So instead of putting x here, this is called a VT graph, or a velocity time graph. And we can look at how the velocity changes. So for example, if let's say this is 5 meters per second, if I have a graph like this, is the velocity changing? No, right? The velocity stays at 5 meters per second. So, what's the acceleration? Well, the change in velocity is 0 over, no matter how long you take, 0 over anything is 0. So there's no acceleration. All makes sense, right? Easy, okay? However, if the velocity changes, right? So if it goes like this, right? So I need to know how long it takes, right? So let's say it goes from 0 to 3, and it goes to 15 meters per second, like that. Let's say it goes to 20. Okay, so what's the change in velocity? The change in velocity is 15 meters per second. The change in time, right? The time taken for the velocity to change 15 meters per second change, right? This is the amount of change. So this one subtract by this one change is 5 seconds. So what is the acceleration? In this case, right? So the acceleration A is 15 meters per second divided by 3 seconds. Sorry, why did I say 5? 3 seconds, right? Everything is in, let's say, meters and seconds to keep things simple. So the answer is 15 divided by 3 is 5. So 5 meter per second per second. Okay, so there's a couple of ways you can write this. You can write this in a confusing way like this: meters per second, that's okay. Or meter per second square, that's also okay. Or meters second to the power of -2. All of these are okay. Of course, the bottom two are preferred. That just looks convoluted, and that just looks ugly with different seconds levels, right? And you either just do one fraction or something to the power of -2, which means on the bottom of a fraction, right? So those are all okay. We of course prefer that. Sometimes I just want to emphasize it's 5 meters per second, right? So it means that every second, when it's 1 second, it increased by 5. So it went to 10 meters per second. The next second, it went to 15. The next second, it went to 20. So it went from 5, 10, 15, 20. Sorry, not to scale. Yeah, so it increases 5 meters per second. Okay, so sometimes when we're reading it, we'll say 5 meters per second, something like that, or 5 meters per second square. That's more concise, but sometimes I want to emphasize it's how many meters per second, right? And it could be, these two doesn't have to be second, it could be 5 meters per second per hour. So each hour, it increases 5 meters per second, or 5 miles per hour per second. So each second, you're accelerating 5 miles per hour. That's a pretty large acceleration for a car, but yeah. So it's basically length per time, right? So that's the idea. Okay, good. So again, let's look at average versus instantaneous. In this case, what am I calculating? Is it average or instantaneous? Can you tell me that? And if you're thinking both, you're correct. Because notice one thing is, if this is a straight line, then the average, right? So you just take this, so this height divided by this height. So technically, I'm calculating the average, but at every instant, the tangent is the same as the overall slope. So we actually notice one thing, right? Let's summarize this. Important fact is that if the velocity, if the VT graph has a straight line, so if it is a straight line on the VT graph, is the better pen for this? Then A average is equals to A instantaneous. Okay. And also notice the first second over here. What's the acceleration? The acceleration in the first second is 5 meters per second per second. The second second, the acceleration is also 5 meters per second per second. Let me not write the units here. And then A is also 5 meters per second if I go in a straight line like this. So the A is constant. All right. So if I plot this out on this time, the last but not least, the AT graph. So we have an XT graph with VT graph if you want to analyze how the velocity changes. If I want to analyze how the acceleration changes, what is this? Well, it just stays at 5 meters per second, like that, right? Like I said, when I'm teaching, sometimes I want to emphasize it's 5 meters per second. But when you write in an exam at the final answer, you want to just write it in a more condensed way, just for readability purpose. But for conceptual purpose, sometimes I want to emphasize this, right? It's a straight line. So the acceleration is constant. So we say A is constant. And this is what happens in the VT graph if A is constant that way. Okay. All right. So this is also true, by the way, if it's a straight line on an XT graph, it means the velocity is constant. So let's put that down as well. If it's a straight line on an XT graph, equals to constant. Okay, let's make sure this is true, right? Let's see if I draw a xt graph, and if it's a straight line with some slope like this, and that means remember velocity is the slope on xt graph, right? The average velocity is the average slope. The instantaneous velocity is the instantaneous slope. But if it's a straight line, then the average slope is the same as the instantaneous slope. At every single point, the slope is the same, right? And the average, of course, average meaning average, is the same. So V average is the same as V instantaneous, and it means that the V is constant, or this means A is constant, like that, right? All right. So this is fact number 1. And fact number 2, so what we learned is also the velocity is the slope on the xt graph, and also the acceleration is the slope on the vt graph. So I'll write this out. So acceleration equals to the slope on a vt graph. Again, you can see from the definition, dv like this, right? So this is average, and instantaneous is dv dt. It's the lazy way to say the limit of when we look at the t is 0. And velocity, this mirrors exactly what we've shown, or what we've discussed. This velocity is the slope on the xt graph, because it's the rise over run. Okay, I'm gonna get tired of writing average velocity. I'll show you a symbol in a second. I'll add to it in a second. Is this, right? Instantaneous dx dt. All right, so you understand this as rise over run. So you see that its velocity is the slope on the xt graph. So you just look at this part, right? It's the slope on the xt graph, and acceleration is the slope on the vt graph. So instantaneous just means the precise slope. So if this is changing, then you want to look at the precise slope at that point. So that means the tangent at that point. And you need to use the idea of calculus, which is basically shrinking the denominator to 0, right? It's shrinking the reference point to 0, reference time to 0, if you like to think about it that way, right? So that's the idea of calculus. Sounds like a very fancy word, but that's really the essence of it. If you can understand that, then you understand the concept of calculus. The rest is just some rules to basically do the math, but we'll get to that. We won't do a lot of that, but you'll see it's extremely simple if you can get this, right? All right, yeah. Lastly is notations, because we're lazy people. So instead of writing average every time, usually in mathematics, we put a bar on something, and that means average. And that means I can leave out and not write a subscript there, and that means the instantaneous. Okay, all right. So yeah, while we're at it, if you like, let me change this as well. So I can write this as average equals to this equals to constant, right? So if it's a straight line on the VT graph, you have the average velocity, average acceleration is the same as that. And if you have a straight line on the XT graph, what does that mean? That means, well, the slope of that, right? That means V is a constant. And that means the average is the same as the instantaneous V, which is a constant number anyway throughout the time. Okay, all right. So we'll comment on a couple of extra things about acceleration. Mainly, I want to define properly what does deceleration mean, and it'll take us to studying how we can put all these together and analyze motions once and for all.